All right. Orthogonal is just a fancy word for perpendicular. So if their dot products between two vectors is 0, then we say they're orthogonal. Okay? So in all three of these cases here, we're going to check and see if they are orthogonal or not. If they're not, we're going to cross them out. All right? So v dot w here is going to equal 2 times 3 plus -1 times 6. So we get 6 plus a -6, which equals 0. So double check, we got 0. That means it's orthogonal. For b, we got 1 times -1 plus 1 times 1. So that's going to equal 0 also. Boom. That guy is a 0. So that's orthogonal. And c is kind of a special case. It's also orthogonal. We have 1 times 0, because there's no I here, plus 0 times -3, so they all equal 0. Another thing you can note is that these two mean they only have one component. So if I were to draw I, it would be this red vector here. It only sits on the axes. If I were to draw W, that's going to be -3j. It's going to look something like that. Well, they're sitting on the axes, and the angle between two axes is always 90 degrees. So anytime you see lone components as a vector, you know that the two of them, if they're on different axes, are also orthogonal. It's just another thing to look for. Okay. Alright, so now we're going to learn to break one vector apart into two orthogonal vectors. So what we have to do is we have to create a projection of an original vector onto another vector. So in this problem here, we're given w, this little vector, which is represented by I plus j, and then we have this vector v, which is I plus 3j. Okay, and v is right here. Okay, what we need to do is we need to treat v like we've shown a light down, sort of a parallel light. Imagine there's a flashlight shooting down here and we have this shadow created this long. So perpendicular flashlight shooting down on sort of some rod, and it creates a shadow. That shadow is the projection onto w. Okay, so what it does is it creates this v1, which will be a component of v, and then perpendicular to that will be v2. Okay, and in order to do that, we need to first find v1. Oops, let me change colors here. We need to first find v1, which is going to be represented by v dot w over the magnitude of w squared times w. So this whole thing will be a number, and then you'll multiply it by, in this case, I plus j. Okay? And then v2 is simply taking v, your original vector, and subtracting the new vector v1 to get your v2. Okay? So in this case, what we're going to do is we're going to find v dot w first. V dot w is going to be 1 times 1 plus 3 times 1. Okay? Which is going to equal 1 plus 3, which is 4. And then we need to find the magnitude of w, which equals the square root of 1 squared plus 1 squared, which equals root 2. Okay? And then we're going to square that, which will leave us with 2. So this whole thing, this whole part, this whole chunk, in this particular problem, v1 is going to be equal to 4 over 2. And we're going to multiply that by w, which in this case is I plus j. So we're going to get 2i plus 2j. That's our v1 vector. In this case, if I were to draw this in our v1 vectors right here. Okay? 2i plus 2j. All right? Which makes sense because it looks to me like they've got 1, 2, 1, 2. A nice little situation there. Alright, so that's set. Now that I have V1, I need to solve for V2, which is merely V minus V1, or in this case we've got 1 minus 2I plus 3 minus 2j. So V2 then equals negative I plus j. So we found our two vectors, V1 and V2. Okay. All right, our last example involves force and work. Okay, so here we have a girl pulling a wagon with a force of 50 pounds. That 50 pounds is represented here, where her arm is pulling it. Okay, and then it is sitting at an angle of 30% from the parallel with the ground, from being parallel with the ground. So that means that not all of the work is happening in the horizontal direction. There's some force being kind of wasted, if you will, on the vertical. But it's obviously necessary because you can't hold your hand down there. So what we want to do is determine how much force or work is being done on this thing. And so in order to know that, we need to know what the force is in the direction we're moving. And then we also need to know our distance vector. So we need to know basically how far we're pulling it. So, and then the dot product between the force vector in the x direction and the distance vector in that same direction creates our work. Okay? So in this particular case, that's going to look something like this. We'll say that work, W, equals force dot AB, where A is our starting point and B is our ending point. Okay? Alright, so first things first, we need to create a vector from our force vector. So F is going to equal the magnitude of F here, so 50, times cosine of the direction angle, so 30 degrees, I, plus sine of 30 degrees, J. So then F ends up equaling 50 times root 3 over 2, I, plus 1/2 J. 1/2 J. Alright, so then we have F equals 50, let me write this somewhere else. So we end up with F equals 50 root 3 over 2, which we can actually write as 25 root 3 I plus 25J.
There will be no practice today for the...
Alright, so the next thing we need to know is our distance vector, our A to B vector, if you will. We just found the F, we need to know A to B. Well, A to B is a vector based off of where you're moving to. We have a starting point of 0, 0 here, and an ending point of 100, 0 here. Okay, so in order to create a vector from that information, we just take 100 minus 0, I, plus 0 minus 0, J, and we get an AB, equals, so AB simply equals 100 I. Oops, gosh, I keep writing that J as an I. Be careful. 100 I. So we have a vector going 100 I in the x direction, and then in order to solve for work, we take the dot product of those two vectors that we just created. 100 I dot 25 root 3 I plus 25J. Okay? Well, again, we don't have any J, so the zeros cancel each other out, and when this dot product is created, we end up with W equals 2,500 root 3 foot-pounds. Okay, and so 2,500 root 3 foot-pounds, and that comes from the fact that our force was 50 pounds, and that we moved 100 feet. Okay, and we're multiplying, so foot, it's not foot per pound, it's called foot-pounds. So I'll try that again, foot-pounds.